So I think will work. Do you guys see slides? No? Okay, not sure if I hear you guys.
I can see your slide and I could see it in full screen.
Okay, great. So you can hear it?
Yes.
It's just that you guys aren't moving.
Everything is in full screen now.
Okay, good. Then all right, sorry for the delay. Hawaii and Brazil are slightly different time zones than I think initially thought. So thanks for bearing with me. So I was asked to talk about LSST, the Large Synoptic Sky Survey, the Large Synoptic Survey Telescope, and I'm co-chair of the Solar System Science Collaboration. So, my role is sort of helping to steer the planetary community towards what we can do with LSST and ensure that what we want to do, we're able to do with LSST. So I don't know how many people are really familiar with LSST, but I wanted to put some introductory slides in. LSST is really going wide. It'll have a couple deep drilling fields where they're going to target. But the point is to be what they're calling this wide, fast, deep survey where they're covering about 18,000 square degrees, getting precision of 0.5 to 1% photometry in GUR, I, and Z, and Y. So there's that. And that it is observing over multiple nights in several different wavelengths. And also the point is that it'll image the visible sky every 3 days for 10 years for the nominal baseline. So the data deluge is coming. I mean, it's roughly 20 square degrees within 3 to 14 day cadence. It's 800 visits per field over 10 years, 6 million asteroids, 8,000 lensed AGN, 10 to the 4, 10 to the 5 galaxy scale lenses, and 4 billion galaxies are going to be imaged. So I think, as in my head at least, I can't quite quantify these numbers. I can't have a sense for them. They're that big. So, I think that, we really are sort of going to a new stage of astronomy, sort of with this large data set that's coming of observations greater than 16th magnitude. So brighter than that, LSST will saturate. 4 key science themes are constraining dark energy and dark matter, taking inventory of the solar system, so the one that I care about, exploring the transient optical sky, and mapping the Milky Way. So those 4 themes are driving all of LSST's cadence, science, and main sort of parameters. But there are many other science collaborations that are, there are 8 actually that are feeding into this. But again, sort of what's kicked off LSST and what their core aim is to get those 4 in some way. So I just wanted to talk a little bit about the camera. It's going to be a 3.5 degree field of view with basically these rafts that then get made to make the full field of view. So this is, they're already started construction on the rafts, and the commissioning camera for LSST will be one of these rafts, and then the full focal plane will be sort of filled in the full camera. So, sort of coming on scale, I work at Gemini Observatory. So for me, this figure is kind of nice to show how we're going from 8 meter, but we're an 8.2 meter, but LSST is an 8.4 meter, and by changing the secondary and tertiaries, you're getting this 3.5 degree circle in the sky. So sort of showing the field of view for GMOS at Gemini South, and compared to LSST's field of view. So I think for solar system, this is sort of unprecedented to get this kind of field of view at 25th magnitude. And LSST is complicated because there's a lot of data products that have to get created. So this is just how sort of the data processing sort of infrastructure that it has to go from the observatory control system to sort of having an alert stream of data that comes up very quickly on a nightly basis, and actually after every observation, to sort of full data releases that are come annually, and then also calibration products, with having ability for people to be able to access these for those that have data rights. So for me, LSST, ever since I've been in grad school, has been this thing that's sort of on its way, but so far in the future that no one cares in some sense, right? Like, it's so far off, and now 2020 doesn't look so far off for first light. It's really coming together. So the bottom is the artist rendition of the mountain, and then on the top is from December. And so it really does, starting to resemble that artist rendition. It really does look like what we were sort of promised. And so, it's 2018, 2020 doesn't seem that far off. 2022 is the start of science operations. It really is now sort of on the horizon. And I think that point got driven home for me this morning when I looked online and saw that there are pictures tweeted of the construction on the dome itself. So you saw in the last image, it's sort of, they've got the sort of base of the dome, but now they've actually started putting in the structures that'll hold up the rest of it. So this is really happening, and so we need to be prepared for it. If you are in the LSST science collaboration, or if you're not, there's a couple ways you can get access. So I just sort of stole this from Beth Willman, but there's the News Digest gives you sort of a broad overview of what's going on. Community.lsst.org is where you can actually post questions, talk to the science project team, as well as people from corporation. And then if you're in the science collaborations, there's also lsst.slack. So each of those science collaborations has their own Slack channel where you can ask questions or also interact with more people from data management, for example. So there are a lot of ways of communicating, some better than others, but there's pathways, as well as sort of talking to your collaboration chairs and going that route as well. So I want to talk a little about what LSST is going to produce for the solar system. So this has come from the LSST science book. And these were simulations done to sort of look at taking what we know about the populations in terms of size and magnitude distributions and orbital distributions, and populate through sort of a couple of default vanilla LSST models for their cadence. And what we're really finding is it's huge numbers of asteroids. It's 10 to the 5 in the range for Jupiter Trojans, and then for Kuiper objects, we're in like 40,000 objects. We're getting into millions of asteroids, and as well as doing a good job of picking up some near-Earth asteroids. And if you combine LSST with other surveys for near-Earth asteroids, about 80% of the potential hazardous impactors or possible impactors in the size greater than about 350 meters should be picked up between all of these surveys together. So that was one of the, that's sort of important, I think, as well. So here's just showing that in a better table, sort of showing 90% completeness, 50% and 10% completeness. And so we really are getting this very large sample of objects. I mainly study the outer solar system, and for me, we only know about 2,000 objects with good orbits. So getting 40,000 Kuiper objects, and that's not including the scattered disk where they didn't even put estimates, is a lot. And so we're getting into way order, at least an order of magnitude more objects. We will test things like Neptune migration models in detail, or color distributions that we haven't been able to do in any other way. So that's sort of at least why I think we care about the solar system with LSST, is because it has this ability to find large number of objects and really get us these order of magnitude effects, that we can now study by having all these objects, and the precision photometry and what all these additional things that come from it. The scary thing is this is coming very close, as I kind of mentioned. So 2018 is the first data from the auxiliary calibration data comes from the auxiliary telescope. 2020 is supposed to be when the commissioning camera goes on. And by 2021, the first on-sky and calibration data from the full camera with all the rafts in 2021. And then by mid-2021, we're in science verification mini surveys. And so that may be where they ask science collaborations in the broader community for ideas to test out the pipelines and system. But they haven't kind of gotten quite there yet. So, I mean, it really is coming out down the line. So if you're interested in LSST, this is kind of the time to get involved while there's still chances to sort of impact some decisions and cadence and other things. So for solar system data products, what we care about is that, and I'm still on this from Mario Urim, is that there's 10 million time domain events per night detected by LSST. And so these will come out 60 seconds from an observation in an alert stream that can be picked up, and people can parse however they need to trigger telescopes or follow-up observations. You know, for example, Gemini South is on Observatory, and it's right next door to LSST. If there's a supernova, you might want to slew Gemini South immediately, for example, and follow up as fast as possible. So that's sort of the thinking for having this alert stream, is that you can do these really rapid follow-up events. For solar system, all of our objects will be in this transient pipeline. So in what they're calling prompt data products will be the alert stream, where every 60 seconds you will find out all the transients that are in the image just taken. But there will also be a catalog of solar system bodies. So nightly it'll link what it can in the moving object pipeline to identify solar system objects. But within the alert stream, solar system objects will be in there, but maybe not necessarily labeled as being a solar system object if MOPS hasn't linked it yet. But that means you can do other things if you don't want to wait for the moving object pipeline. For example, for near-Earth asteroids, you might want to go sooner. If you know their objects are elongated, you can do work without having MOPS do some of it for you. So the data release versions are going to be annually, and these are going to be, approximately 7 trillion observations or sources, 30 trillion measurements. I can't even fathom that, but that's what LSST is going to give. So these are going to be annually. They're going to be reduced from both the single images and the deep co-added ones. So this is where you're going to get your precision photometry, not necessarily going to get that from the prompt data products. And then user contributed is LSST's idea of added value stuff that other people write because you need to do your science. So LSST is going to provide moving object detections for the observations taken. But if there's a deep drilling field and they're saying coming back to the same place, for example, for doing supernovae or microlensing, you could stack those images, stack and shift images to identify very faint Kuiper and small Kuiper objects that would go well beyond the LSST limited magnitude in their images. That's not something LSST is going to produce, but it's going to have the data set for you to be able to do it. So user contributed data products are writing that software and coming up with those detections, for example. So what are the LSST deliverables for solar system science? I talked about them, but just to sort of summarize what is sort of maybe a little bit different about solar system compared to some of the other collaborations is, so after 60 seconds, in that alert stream, you're going to get data about those objects, including trailing, direction of motion. And then every day, MOPS, the moving object pipeline, is going to link those tracks of individual transients and send, if it can identify something it thinks is a moving object, it sends it to the Minor Planet Center. So all LSST detections are public in some sense. The best photometry may not be yet, because that will take the annual release, which will not be immediately released to the public. It will be, or to the community, it will be people with data access initially, and then we'll have a proprietary period. And then every day there's a catalog of LSC discovered objects. So every day you'll be able to query that database to find new objects that are detected. Those will all be in the Minor Planet Center. So the way the LSST moving object pipeline and data management will work with the Minor Planet Center is being discussed, and they're trying to figure out how best to make sure everyone has the most information. And then annually, that really precise catalog, that 5 millimag systematic limited catalog, will come out. So with other collaborations, their data sets may be protected in a different way of that proprietary period, but all LSST projects, solar system products in some form, are public via the alert stream or Minor Planet Center. So we're in a sort of a different boat of that detections are public, but not necessarily other data products that would help you do your science. Like if we wrote a detection efficiency pipeline that puts in a population through everything, that might not be something that's available to people not in the science collaboration. But those things haven't been written yet, and those decisions haven't been made. If they're made, if this is software produced by the Solar System Science Collaboration. But in terms of what LSST is finding, that will be immediately in the Minor Planet Center. So how is LSST doing this? So they're basically, there are at least two observations on a given night, and those are linked to make individual tracklets, and those tracklets are then linked into tracks. There's Mario Urim at University of Washington is leading this endeavor, and so he, in data management, he's also a liaison, but his main priority is to get MOPS fully operational. So at some point, the moving object pipeline MOPS was sort of on hiatus for development, and was sort of been sitting sort of on ice. And so now officially MOPS development is active again, and they're working on actually getting this moving object pipeline working with this wiki transient factory. So we've got a date which is going to produce sort of not the same amount, but it has a cadence that will produce similar rates at similar types of alerts and variants and transients. And so the LSST is using this as a test bed for the moving object pipeline, among other things. So this is really, they're trying to apply MOPS now, so we're ready for when LSST has first light. So again, all those moving object data, those orbits that are fit will be sent to the Minor Planet Center. So everything that it's found by MOPS will be sent as quickly as it can be. I think what's interesting and sort of where people can get involved right now is that LSST cadence is not necessarily fully decided yet. So there's a broad idea of what's happening, but they're actually, the way that they will decide the final cadence is that each collaboration will come up with a set of metrics, some quantitative way of saying, if you achieve this, you've hit our science goal, whatever that science goal, whether that's detecting 5 million asteroids equally distributed on the sky, or whatever, finding 10,000 objects in resonance with the 3 to 2 mean resonance with Neptune, whatever is that metric, it will be coded up, and then they will apply these operation simulations, which are basically simulating what LSST will do on sky, assuming bad weather and time of day and everything, and then run a test of either populations or simulating supernovae and saying, yes, when you hit this metric, how many times has this simulation hit the metrics for solar system, for supernovae? And so they'll pick the best cadence that satisfies as many or as best as possible the requirements that are being suggested by the science collaborations in terms of what their science or highest science priority needs are. So this will happen in the next few years, and it will actually be a Science Advisory Council, which is independent of the science collaborations, and their members are supposed to represent the community. And so there's ones for sort of in the top, all the topical areas that represent the science collaborations on there. And so they will get the information from the science collaborations, see the results of the simulations, and then they will suggest and recommend what the final cadence should be. So OpSim is sort of the way now that you can play with these simulations, and eventually we'll code up this matrix and metrics to make those final decisions. And so it's on the way. I mean, by 2020, the final, these metrics analysis framework has to be completed. We need to, by 2021, the survey strategy will be set. And so we have a couple of years now really to sort of understand what are our science priorities, what matters most if we have to give something up in cadence, and ensure we're going to get solar system objects. And part of this is that There will be deep drilling fields that will LSST will focus on and come back to every night, as well as mini surveys. And so one of them is actually probably no way to see a mouse, but you see that sort of purple bit above north of the ecliptic as northern ecliptic spur on it. That's actually a proposed mini survey. So that would be to get the rest of the ecliptic for the solar system, because otherwise we're missing half the ecliptic and a large number of objects, because a lot of things will be lying on the ecliptic. As well as for the outer solar system, we will miss the half of sort of either the leading or trailing resonances with Neptune. So it's important to sort of get that. But that's been added as sort of a mini survey because they realized that. But in this year, we're going to actually have to justify that in terms of the solar system science. And so anyone will be able to propose a mini survey, whether you're in the science collaborations or not. And you can write a white paper suggesting a deep drilling field with it repeats observing that field, or a mini survey like the northern ecliptic spur, sort of covering a different area or in a different way than the main survey. And so these are going to basically be asked for in about June. They're going to put the call out, I believe it's early summer about, and then it'll be due sometime by the end of 2018. So if we don't know what our science priorities are and what we think we're going to get from LSST, the main LSST survey, it's going to be hard to sort of respond to these things in the most effective way. So that's sort of what's been on my mind, is sort of helping to lead the solar system science collaboration, is that making sure we're ready and that we don't miss an opportunity that could really help us and our science. So for the LSST Solar System Science Collaboration, we have a website. You can go there and check it out. David Trilling and I are the co-chairs, so if you have questions, you can always feel free to email us. Other collaborations have different chairs, but that's ours. And we have a full website which has information. So we've been trying to keep this as sort of a portal for ways of sort of putting as much as info we know about solar system data products and operations from LSST onto the site to make it easier for us later on as we try to write these proposals and white papers, but also just sort of to keep it all in one place. So our collaboration is sort of split in different ways. David and I are the co-chairs, and then we currently, we now have, as of last year, working groups. So we have active objects group, basically comments, anything that goes bang in the night, with Alan Fitzsimmons. We have a community software and infrastructure group, development working group. So that's led by Henry Shea. And the idea is basically get everyone who wants to do and write software together so that they're talking to each other. We have an inner solar system group. Broadly, it's the asteroid belts and Jupiter Trojans and irregular satellites of Jupiter. Near-Earth objects, we also stuck in interstellar objects because Oumuamua showed up and we figured it fits better within near-Earth objects. So that's being led by Steve Chesley. And then we have outer solar systems, so again, mainly Kuiper belts, Planet 9 stuff, satellites of the rest of the giant planets. So we kind of broke it into different populations. These working groups may not stay that way, but we figured primarily right now that seems like the right way to go, rather than saying there's a light curve group and there's a surfaces group and there's a dynamics group. But yes, we have overlap, but like at least this way we can, since there are different constraints for how you find these different populations, that was a good way to start off with. So maybe in a year or two, when things are closer to first light and of the full survey, then maybe we will change the structure. But these are the people to go to if you have questions about the specific sort of working group topics. So we've kind of tried to ramp up our activities in the last year since I've been co-chair as of May of last year. So Lynn Jones stepped down. I took over her position as co-chair, and David Trilling at NAU continued on. So we now have a new website. We established working groups. We adopted a code of conduct. We've drafted a charter that's actually now passed as of last month. So we now have a charter. We restarted the science roadmap. I think that's been really big because the idea is to have a list of what are our science priorities in order and by priority, so that if we need to give something up, we know what we're willing to give up and what we're not. And that way, when another collaboration says, I really need this to do my science, we can step up and say, no, you're going to lose our top science priority by doing that. like we can, we can't have you do all of that way because we'll get this is our highest priority. Or maybe it's our lowest, and then we go, yeah, sure, if you get rid of that, but you keep the northern cryptic spur because that's what we need to do our science, or it's our top ranked priority. So by having a roadmap, we can start having these discussions better than David and I making assumptions based on what we know, because we don't have any direction from the rest of the community. We've also tried to, and there have been past solar system workshops at DPS, so we had one this year, and then we're starting to actually talk to data management about what we need in terms of content for the solar system database schema. So what values are going to come out of that alert stream, or what going to be easily accessible, or things, about solar system objects, orbit, magnitudes, etc., as well as, what things we're going to be expected to compute. Like everything's going to be in heliocentric coordinates, but there's half the outer solar system would prefer barycentric. Inner solar system people want heliocentric, and then half the people don't know how to do it. Or rather, they could find a tool to do it, but they don't necessarily have one right off the bat, but they usually fit their orbit one way or the other. So we know, just from polling our collaboration, we already know that that's something. By having these discussions with data management, we know that's something that we're probably going to have to make as a tool that will take every orbit and convert it to barycentric. So people that want to use barycentric coordinates or orbits have that ability. So by starting to have these conversations with data management, we can start sort of learning these things. So I mentioned the science roadmap. It is out as of last week. And so it's 7 pages. It's on Astro PH, so you can get it on the archive. And the point being here is to really just sort of bullet point out what are our top priorities, so that we can then start coming up with these quantitative measures, sort of to decide when has LSST successfully achieved that goal for solar system. So I encourage you to read it. We plan to make this a living document that, as we get these metrics, we'll put them in and sort of continue to build this. So it's sort of our first go at this, and I expect it's going to change a little bit between now and 2022. We didn't know about interstellar objects and the Planet 9 theories until, recently. So those things are not even in the LSST science book because we didn't know about these things or didn't and weren't thinking about them as much. So these are some of the priorities just to float through. I showed these at the DPS meeting. So they've changed a little bit, and they're not necessarily in order from what's in the full roadmap, but just to sort of give some idea of some of the things that are in there. So we don't have to go through them, but for NEOs, near Earth asteroids, they really want a high completeness catalog with really good orbits and quickly getting those objects. And people want to know about rotations and shapes through light curves, and really want to know timely, at least for near Earth asteroids, really want to know timely approaches of objects, so that they can do other observations and facilitate follow-up with Arecibo to get radio and other things. In our solar system, discovery is one of the highest, and it still is, that they want all the populations, as many objects as they can get. They're really into doing light curves and shape models. Again, color and composition through getting for broadband colors. Outer solar system has the same thing. Discover large numbers of objects, light curves, orbital classifications of objects in usual orbits. So can we prove or disprove Planet 9? And also that stellar occultations has been really important in getting sizes for covered objects. So they want really good astrometry coming out of LSST, which it's going to. The active objects group really wants to find tons of active objects. They are really interested in, again, finding activity levels and monitoring activity levels throughout all of the orbit of these objects. So something that LSST can do with a 10-year baseline, sort of using the same telescope in good conditions. And also sort of find things that are unexpected. So if they know if something's very anomalously bright compared to what it should be, that they can start triggering other telescopes to follow up to see what's going on and things like that. So that's sort of the broad scope, paintbrush of the science priorities. You can read the full science roadmap to see them in detail. And for me, what's come out of it, it's been interesting, is that the numbers of objects is a high priority for every working group. Everybody wants a large number of objects. And so for the first time, I actually have an argument for why we need the northern ecliptic spur, is that we really want numbers of objects. And that's our highest science priority goal. And so we are willing to give up a little bit of something else to get the northern ecliptic spur, where although LSST will not go back as often or in as many colors, losing that space means we lose a lot of objects. And by finding objects, we can do a lot of orbit stuff that we can't, and population statistics we can't do without them. So that was something that I didn't necessarily think was going to be the top priority for every science every working group, and it is. So now we can start having those kind of discussions. So that was a big thing for 2018 for us to sort of finalize that roadmap and get it out. So now we are starting on developing metrics for those priorities. So going through each one of the bullet points and saying, how many objects will make you happy? Is it 10,000? Is it 5 million? Is it 5? And coming up with that number. And then give input and finalize with data management what the solar system database schema should look like. So are we getting ecliptic coordinates in there? What are they outputting to us? Are we putting multiple photometric apertures for people that are doing comets? That might be more useful than us having to go take those images and do that. Would it be better and faster for that information to be there ready? We need to plan and make sure we're ready for those deep drilling fields and mini survey white paper calls. So I think we're on track by getting the science roadmap. We'll start thinking about those metrics, which will then help us decide what things maybe we can't do with the cadence as is. So maybe we want better colors, because colors are going to be coming from whenever LSST decides to image that field and our objects rotate. So maybe you want to do something with a deep drilling field where you stay at the field and rotate the filter wheel, and stay there and rotate, and then you can come back later and do the same thing. And that way we've got all the colors in a way that we can then take out some of the light curve effects. So that's something that we can propose for now that we can say, sort of feed back to that roadmap and refer back to it and say, well, that's a priority. LST's wide survey is not going to do it in this way. We would like a deep drilling field to do this, and it's going to give us better science than, a different and although smaller scale for doing these really tough questions. So that's sort of where we're headed this year, and then really to start working on getting that added value data software. So one is that we need to write that conversion to barycentric coordinates because it's clear people want it. And also sort of coming up with simulated data sets to test and think about how do we want to do a survey simulator with LSST. They're LSST is mainly going to provide us with, here's what their detection threshold was, here's where how MOPS performs with different orbits, but not necessarily putting everything together. And so that might be something that we need to do, or coming up with populations that maybe they're not necessarily going to test. And so I just want to end a little bit with a case study, because this is sort of what's keeping me up at night right now, is that Oumuamua, and if this works, is the first interstellar asteroid. And so it came in, it was sort of within the orbit of the terrestrial planets. And so it's on a hyperbolic orbit, and the only way it can be on a hyperbolic orbit and not have interacted with Jupiter is to be actually not from our solar system. And so it came in basically almost perpendicular and then was bent around as it came by the sun. And it was only detected after its close encounter with the sun. So it was actually found by Pan-STARRS, which is a 2-meter telescope that I've been observing for, I think, a decade now, or at least 4, 5, 6 years now on Haleakala. And this is important because Pan-STARRS can give us some limits for LSST. And so that is sort of one of the interesting things of that. People had started writing papers about limits for finding interstellar objects. But they were pessimistic to maybe LSST will find one, to LSST is going to find lots of them. So now by having one that we know is some object from another solar system that we can sample its planet formation processes by studying this object, we have a data point you could start trying to scale up based on some assumptions. So it's kind of really exciting that Pan-STARRS found one, because it gives you a lot more hope that LSST is going to at least find one. And the interesting thing about this object is that basically the entire world scrambled to study it. Both Gemini North and South. I was involved in a program in North. We had 3 director discretionary programs between North and South studying this object. There were Euclid, VLT, everybody was looking at this object because there was about a week and a half that this object could be studied before it was too faint to even get it with 8 to 10 meter class telescopes. So, to really understand this, you want to get light curves, you want to understand if there's cometary activity, so you want to be able to get deep stacked images. And if there is activity, you want to see how it evolves. So getting on these objects, you need to get on them fast. And I think this was interesting for the community because I think lots of different groups got involved. And if Kuiper Belt observers like myself were getting involved, comet people, the near Earth asteroid community, so lots of different groups because we all had sort of something to throw at this object based on what it looked like. So people were doing deep stacked images to find out that it doesn't have a tail. It's not a comet. It's actually the first object to be classified a comet and then declassified. So it was actually, they call it an interstellar comet, and then there was no coma, and so it's an interstellar object. It's a very flat, slightly red spectrum. Looks very much like a faint Kuiper object, a 22nd, 23rd magnitude Kuiper object. So when I saw this on Twitter in similar spectrum, I was like, oh, that looks very much like why people do broadband photometry in the solar system. And then that's why we, my collaborators, Wes Fraser and Michelle Bannister and Michael Mercier and Rosemary Pike got, among others, got Gemini time to compare Oumuamua to in J-band with some optical observations to our survey for other Kuiper objects in similar bands, as well as other solar system objects. And the spot is busy, but the yellow diamond is the sun, and then Oumuamua is that red star. And the point being, it looks very vanilla. It's slightly redder than the sun, but looks very much like some of the Kuiper objects in our survey, as well as the Jupiter Trojans and Jupiter family comet. So it's a little bit, if I hadn't told you what it was, you would have thought it's probably like a Kuiper object or Jupiter Trojan, Jupiter family comet. So, it's kind of exciting that we can do these things if we know about these objects fast enough to get them when they're bright enough. For example, for our Gemini program, we got this object on the last night we could observe it before the moon was going to be in the way. And then it would have been too bright. The sky would have been too bright, and then it would also be blocking the object. And after the moon moved, it would be too faint for us to observe. And this object turned out to be really weird. I mean, it's tumbling, so this should actually say accepted now. But Wes Fraser looked at this object and noticed it's actually tumbling when you take all the data. So the data points are different observatories, different wavelengths of all the observations that were coming in. And that sort of simple model doesn't work. So it's actually tumbling, and that's something that looks to have been imparted in its own solar system. So a collision of some sort of something that kicked off that process. And this is just showing Juhas as well, shows the same thing, maybe a little bit clearer. So the red observations are from one night, sort of phase folded, and then the blue are from a different night. And you can see the peaks and valleys are not quite the same. Again, showing that hinting of tumbling. So just by getting all these observations, we're able to sort of understand this object, or try to at least put it in context with our solar system. And also, people were able to get radio observations of it and find out that there's no radio signals coming from it. So Oumuamua is the first interstellar object, but there's many more to come. So based on one object, a lot of the observations now that you take more optimistic measurements, limits from them, is that LSST should find about one a year minimum. So in 10 years running, we'll have 10 objects. So it's going to be really interesting because Oumuamua has a size ratio about 5 to 1, 10ish to 1, more like 5 to 1 based on the tumbling light curves. So it's extreme. We have a couple objects in our solar system that have that kind of axis sort of size scale, but still it's extreme. We don't have many objects like it, but nature can produce it. So it'd be really exciting to see, what does another object look like? Is it redder? Is it as elongated? And try to understand these kind of things. And also see if they're outgassing. Oumuamua could have a radiation crust, and that would be thick enough to prevent the solar radiation from coming through, penetrating through to sort of start outgassing of icy material on the inside. So it'd be really interesting to know, is the next object have the same thing? Or do we see it sort of have a tail and outgas like a long period comet for us in our solar system? So that's going to be really exciting. But for me, it's also, how do we organize as a community to do this? So that if we're going to have one a year, and as well as many other interesting things in LSST, how as a community know that this will be all public? These observations will go public, so everyone's going to know, just like they did for Pan-STARRS, their data that goes to the Minor Planet Center pretty immediately, that this is an interstellar object. So for me, one of the things I'm thinking about is how, as a science collaboration, do we best utilize our resources, so that we're not just individual groups triggering telescopes, but maybe using it the best way possible to know where we need additional information. And so we don't have, there are not many sort of tools for doing this yet. And so I think one thing I want to think about, at least in the next few years, is how, as particularly for, say, the near objects, interstellar objects, for people that are interested in that, the cometary group people, how is the best way for us to work together with these large data sets coming in from LSST? So is it that we write these proposals and be ready to go, or do we have ways of facilitating communication such that we are, everyone who's in the collaboration who wants to participate knows what everyone else is doing and what data they're coming in, and sort of agreeing about how we might write papers on this. So I think that's sort of the lesson right now, is to think about, we're going to have one of these a year. They're going to be interesting. But that's just from Pan-STARRS, right? And so that, I'm sure there are other interesting things that we found just with LSST. And so when that weird thing comes, how do we coordinate this? And is there someone we assign to be that coordinator to make sure, facilitate that information's getting from one person to the other? And how best do we want to work together? Or do we want to work together at all? A lot of these observations were done sort of independently, and there's many papers on this. And maybe we want to have them independently, but it's the interpretation that has changed. So Oumuamua was first said to be a 10-to-1 size object. And then with more other people's data sets, it was like, wait, it's tumbling. And if we had shared that all at once, would we have come up with immediately a different answer and then be able to follow up differently? So I just want to think, as a collaboration, be prepared for this. And so this is, I think, the best test example for that, of sort of thinking about, as an odd object that came in that's really interesting, how do we, as a collaboration, if we have a short window for observing it, make the most of it? So I think that's also on the horizon for the Solar System Science Collaboration, which is maybe a little different from some of the other science collaborations, where their observations may not necessarily need to be as timely, where there's only a week and a half where you could observe Oumuamua. So, thinking about all of that, I just want to end with, really, science operations are planned to start in 2022. Things really seem to be on the way, and it's really starting to look like the artist rendition. So like, now's the time to sort of make sure, for whatever your science is, that if you want to do it with LSST, it will get done. Because if you don't talk about it and you don't engage, I think, with the collaborations or through the sort of white paper calls, there's a chance that that interesting science may not necessarily be able to be done or optimized with LSST, because they're trying to balance all these science priorities. And so the collaborations that are ready to go and have their list of things and priorities, I think, will be better off down the road, sort of when the cadence is fully set. So with that, I'll just leave up the information for the Solar System Science Collaboration. Happy to take any questions, and also happy to point you to other people. And I'm not in the LSST project, but I know who to probably point people to if you have questions more about the details of LSST or their pipelines.
Okay, Maggie, thank you for your presentation. We have time for a couple of questions. So do we have questions from the audience?
Yes, I have one. So here is Felipe Ribas from Curitiba, so Brazil, of course. I'm thinking, you talked about light curves and with many filters and everything, but I'm thinking about the range that we can think about. Let's say we have certainly exposure time limitations to achieve the expected magnitude in each filter, and the cadence needs to be quite fast to see all a good fraction of the sky. So what are the ranges that you can think about to, for example, derive the making inversion of the light curves, or sort of that?
That's a good question. No one has done that yet. And that's the problem, is that you want the answer, but we have to do that work. So we don't know, because no one's actually taken a cadence simulation, put in light curves and tried to pull them out. We know it's going to be sparse, but how sparse, I don't know. So I have a feeling a little bit from Subaru data that collaborators have taken, and that they were jumping through a bunch of fields over 2 nights, and you know, they see variability. They're not necessarily getting periods, and that's even like after 2 nights, sort of going through like 12 fields. So there's not a lot of data points, but that's the problem, is that we actually have to quantify this. So that then we can say, and I agree with you, that, you know, a deep drilling field where we go back much more regularly and spin the filter wheel would get us really good light curves and colors with light curve information. So my bet is we're going to have to ask for a deep drilling field to do that, and say, we are not getting as good a science out of your random filter wheel. And so the problem is no one sat down and done this. No one's actually taken OpSim. And that's what we really need to start doing. And so I would love to have someone do that. Lynn Jones has been at University of Washington, is in LSST project, and her main job is getting OpSim working. And she's also implemented some solar system models. So, So, you know, there's some information that's already there that could be taken and used and applied a light curve model, and then for each observation, run it through. But I can't give you an exact number on that. So my bet is we will get very sparse light curves, and we'll get some variability information, but the best light curves will not come from that. So I'm expecting we're writing our deep drilling field will be light curves and colors. But interestingly, that's about third or fourth in the science priorities for everyone. So more detections is higher priority than getting light curves.
Sure. Yeah.
Which I wasn't sure that was going to be the case. I thought I could see colors being much more important than more, like, we're already going to get more objects, but apparently that's the highest priority. So yeah, but it's within the top 5. So I think we have a good, strong case to say every working group said the same thing independently of each other, that light curves are important, and that shape modeling, and that you're not going to get any shape modeling from this. And that's some of the feedback I got from the science roadmap was, well, can you do this? And it was like, that's not the point of the roadmap. The point of the roadmap is, this is what I want in the LSST era. And then we can say, you don't give it to us in the wide survey. We're going to have to do this with some mini survey. So I don't know if I answered your question, or rather sort of danced around it, but that's kind of where we are right now. So I'm hoping we'll have some kind of workshop or sprint in this year to sort of get people in the room, and hopefully someone will work on this and get paired up with Lynn, who knows OpSim and can, you know, take the asteroid population, for example, she already has implemented, and do that. And then hand that off to somebody who folds light curves and say, did you get the right answer? So yeah, so that's my hope, is that we'll actually start doing that. But that's, you know, I could see that being an interesting paper alone, and sort of someone writing that up. But that's the challenge, is that we need to start knowing those answers. So if we don't, or don't even think about it, then we could not propose for that deep drilling field and get really hurt on light curves.
Okay, thank you.
Hi, I have another question. It's Julio.
Hi.
Hi, Mike. What are your tools to map, or to discover, or to catalog the non-solar system bodies that LSST will observe?
Do you mean like interstellar objects, or not moving objects?
Sorry, solar system objects, any asteroids, but that already have an orbit. Do you have any tool to make a catalog from these objects?
So that is being provided by data management. So even known objects will, anything LSST finds will go into the catalog. It'll also be in the Minor Planet Center, so it depends on how you want to get it. And they're trying to figure out the best way. So I think my understanding is now that they will pull in the Minor Planet Center data as well, but also let you know the parameters just from LSST itself.
Okay.
So if you want to know every known objects that are there, that will be something you can pull out of the LSST databases. More fancy things that you want to do with that, we need to write. So if you're really interested in force photometry, along knowing the orbit that you could do better trail photometry than LSST could, they're not going to do that. So they'll do a little bit of that, but they're not maybe going to be as good as if you know actually what the trailing is because you know the rates of motion. So basic things like a catalog with astrometry, they will be providing, and it will be in the Minor Planet Center. Beyond much of that, we have to do.
Okay. Okay.
So example, if you want to know, a residence identification is not something they're going to do. Okay. But Darren Magazine is interested in doing what Brett Gladman has done for the outer solar system and run his software and determine that. And so I'm expecting Darren's going to write a grant proposal to do that, and then there will be a catalog of resonances for inner and outer solar system.
Okay. Because sorry, Nicolas. In some cases, we may be interested in doing our own astrometry for perhaps specific objects. So we are given a CCD with its pointing and the date of observation. We'll have to know whether there is a solar system object there or not. That was just the point, but it's because we use a tool from the Paris Observatory that is installed in one of our local machines.
Well, one thing is that data is going to have to be run on the servers. Mm-hmm. So I think the age of us running things on our own computers will sort of die in LSST because the data sets are so big. So that's one of the things to think about, is that software may need to be adapted because it's going to be run. So basically, there'll be a couple ways of running software on the LSST sort of data servers. And NOAO, at least in the US, is coming up with its own version. And I'm assuming Brazil might be as well, having their own data center. I know, but I'm not sure. I know even LSST UK isn't it's not clear what will be in their data center versus what's in the ones in the US. So that's still sort of being sorted out. What does it mean to have data rights versus data access? So data rights, does that mean you get the raw data at the same time? Or do you get everything that the US people can see? Because we have more resources being provided for data access. So I know that's an argument being brewing higher above, but assuming everybody has same access, I think what's going to happen is you're going to query the database and say, where are my moving objects? And then all the metadata associated with that will be there, the chip, the image, the observation. And the alert stream will have a stamp of the image, observation. So from the straight up alert stream with the difference imaging, you have some astrometry, but you can go back to the raw image, to the image products, and cut out and then do your astrometry or however you want to do it. They're quoting pretty high astrometry. So I don't know if you necessarily need to go back and fit it if they've done a good job on it. So their precision may be good enough for you, I don't know. And that's something that we should find out, because if it's not, then that would be something you'd want to write, or maybe with LSST sort of practicing with Hyper Supreme Cam data, that they will have the precision you need.
Okay.
Meg, I have a couple of questions. I'm Luis here. Two questions. First of all, I mean, I just came back from the Dark Energy Science Collaboration meeting. In their case, they're going to use NERSC. So all the work is going to be in NERSC, etc. What will the other science collaborations do, like in the case of solar system? Because the data center that I understand will be provided is pretty small. I mean, we're talking about 2,000, 3,000 cores for the entire community. Is there a plan?
Well, so the dark energy survey is dark energy collaboration is a very different beast. One is they're basically funded by the Department of Energy, right? And that they've been doing the same things they've been doing for dark energy cameras. So they are much more advanced, I think, than any other collaboration. And also there's a huge buy-in because their data products are all proprietary, that you must be in the collaboration to use them, right? Mm-hmm. Where I don't have that buy-in because all of my data products are public. So you don't have to work with the Solar System Science Collaboration if you don't want to, unless we have something you need. So even in my collaboration, I can't force people to work together. I don't think there's any way I can even force a publication policy where, because why? If you're using a public data product, what's stopping you from using that? Where Dark Energy Survey actually has a very stringent publication policy, right? So they're using theirs because they've already set up for that. I think Solar System, this is the first time we're working together in such a large way. We're still learning how to do that, which is why I established working groups. Like, we didn't have working groups 2 years ago. So I think for us, we're going to have to start off with using what we're getting from NOAO, because mainly we're at least we have a lot of U.S. astronomers. So I feel like there were people using the NOAO tools and using whatever we get from LSST project. If we're starting to find that's not enough, I'm hoping then we're organized enough to then go ask for money to get it. Whether that's from NASA and pull the near Earth asteroid card and say it's really important for that, or in other, pushing NASA that they really need to start funding stuff for solar system stuff with LSST. But most of the people in the Solar System Science Collaboration are not funded. Okay. Where that's not the case with Dark Energy Survey. They're funded. Dark Energy Collaboration, they're funded to do this. I
do understand the difference. I've seen the difference. But my second question is the following, about the broker. Because we're going to have this 10 million alerts, but if I understand correctly, NCSA is just going to stream that to a few brokers. Can be, I think one of them will be in NOAO, the other one will be in Chile. So those are the places that you're going to get the information, right? Not NCSA, right?
So we weren't expecting to get it from NCSA. But we're now at the step that I can start talking about brokers, because now I have a science roadmap where it's clear from both the active objects group and near Earth asteroids they care about this, which before they didn't tell me they cared. So now I think we can start thinking about it, or at least I can direct them better and say, well, you said this was important. Now you need to start thinking about it. So I think we're probably going to be using the NOAO and TARIS is my guess, unless someone gets funding to write their own. Mm-hmm. And I encourage, if somebody thinks of it, go apply for funding. Like, now you've got a roadmap to say these are important, go do it. But our collaboration's very much sort of getting off the ground now. So in my head, I've been thinking it's going to be Antares, but I haven't heard of many other brokers other than, as you said, there's going to be a Chile one. So I believe
the French will also try to.
Right. Yeah. And then there's also room for smaller ones. So, and I don't know what it means to be a smaller one. So I know one of the things that we now have with the science project team is the science collaboration chairs now have a monthly call with the project team, project science team. And so one of the discussions is going to be on the alerts on the brokers. Okay. Like what will they allow and what's going to fit, what's possibly coming down. So it's a very good question, and my only answer is the best I can think of is NOAO and TARIS, because I think that's the one I know most about, and they seem to be a little bit further along than at least the Chilean one, because the NOAO one they're hoping to test on ZTF data by the end of this year. So at least by then, and they were actually, one of the heads of their group was here visiting Gemini, so I kind of reminded them that the solar system people will probably be interested in this too. And they went, oh yeah, we might not have been thinking about that. So I think that's at least where I'm seeing it headed, unless someone in the collaboration or outside of it is really interested in solar system objects and is willing to do the work. So I think that's our difference between dark energy collaboration, science collaboration.
I do have a final question. I was in Chile last December. There was a LSST meeting, in Chile, and somebody from Gemini was talking about some sort of attempt to coordinate follow-up observations. Do you know any more about that? I mean, you mentioned that that would be important, but do you know anybody? Somebody from Gemini, I forget his name.
Brian Miller.
Yeah,
he's an astronomer at Gemini South. So it's not clear how it's going to work because we have partners who are not involved in LSST. So for Brazil, that's great, right? You guys have a little bit of Gemini access, but how other partners may not, and for example, even limited term partners like Korea do not have much access or any, as far as I know, to LSST. That they may or may not want all their telescope time being directed that way. So my understanding is how this will fully work is not 100% decided, but that they're trying to come up with an alert to be able to read the alert stream and then be able to parse it out to all sort of NCOA, because we're all Gemini, NOAO, and LSST, not corporation, not anything that's dealing with commissioning, but essentially what is LSST will be one organization called NCOA because it's all National Science Foundation funded. So the point is that they want to make sure that if you have a trigger from the alert stream, if you could observe that with Los Cumbres, the smaller telescopes, that it would go there. And that the ability that if you could trigger Gemini North if Gemini South was clouded out, or trigger Gemini South.
But it's something that I think could be negotiable because they also have 30% of SOAR, so that would be also an interesting telescope.
Yes, and so that's the point. Yeah, so the point is that then to make it such that you could divide between SOAR and Gemini, and maybe just have a filter and say the entire system triggered. If it's this kind of supernovae, or if it's a solar system object that has brightened by X amount, do this, this, and this. And so Brian's working on making sure we can do that capability, and then how exactly that will happen, whether, some X amount of Gemini time will become LSST pure follow-up, or will that be based on partner? I don't know. But the thought is that we have that capability to do this, and that also North and South are allowed to diverge. So normally our histories have sort of been linked. And so now the board has approved that North and South can sort of diverge in sort of goals and sort of operations behavior. So it maybe South becomes very much in this automated follow-up, triggered follow-up from the alert stream, and that North is more PI-driven, visiting instrument-driven observations for other stuff, and we pick up LSST observation when the South can't do it for whatever reason. Or you need an instrument that we have up in the North. So example, OctoCam is coming to Gemini South, and that's going to be expected to be the LSST follow-up instrument because it's going to be 8 wavelengths, 8 band passes at one go. So it's really meant for transient, though I like it for solar system rotation as well, for getting light curves and multiple filters simultaneously.
So we should keep in touch with Brian, right? Basically, to find out how he's progressing on that, right?
Well, that, and also Brazil has an NGO, right? You have a National Gemini office, correct?
Okay.
So that would be also the pressure to put on, because we meet with them every 2 weeks. We meet with the National Gemini offices. So if there's questions about it, like we had presentations. Brian gave a presentation about what they were doing in the South about the alert stream. So I know they're starting to test aspects of it, and they're now working closer with NOAO because we're going to be one family and organization. So that might facilitate communication a little bit better. But yeah, I mean, also Brian's at every LSST all hands meeting. So he was there in Arizona. So that's also another place to bug him.
Okay.
Or again, in LSST Chile meeting. So yeah, we want to hear from users, right? Because at the end of the day, you're our customer. So we want to make it useful to whatever science you're doing.
All right, will do. Meg, thank you very much.
Have any other questions? Okay, if we don't have any other questions, I would like to thank you, Maggie, for your presentation. And everybody, let's thank Maggie for the presentation.
Thank you.
Thanks very much.
Thank you.
Thank you. Bye.
Bye.